Up to this point, what we've looked at solving is equations written in polar form where we've got z equal to something. We're going to expand on this in this video and start to look at roots of complex numbers. So what happens when we're solving for z squared, z cubed, z to the power of 4, etc. We need to be able to understand how we can solve for this sort of problem. And the reason we're going to ask ourselves this question stems from one simple question we can ask in basic numeracy. Let's imagine we had the equation x squared equals 25 and we wanted to solve this. Now, 9 times out of 10, if you ask somebody x squared equals 25, what's x? They would say x is equal to 5. You know, it's the basic premise in your head. But you've got to remember, you actually get more than one solution. You don't just get 5, you get negative 5. Because if you square the negative number, it deletes the negative part of it, cancels it out, and we're left with 25. So we've got more than one solution to it. Now the same sort of premise comes in when we're working with complex numbers. So let's imagine I give you an equation that looks like this. Z squared equals cos of pi over 3 plus I sine pi by 3. And I want you to get the solution for z. Now naturally you'd think if I've got z squared, great, I'll just take the square root. So z equals the square root of cos of pi over 3 plus I sine of pi by 3. Well, remember, we're taking the square root of this. Now, you'd be forgiven for thinking you could plug cos pi over 3 sine pi over 3 into a calculator, take the square root of the whole thing, and you'd get the answer. We're actually able to get more than one solution for this. What we have to be able to do is think how we would do that, how we get the multiple solutions, and the way in which we can translate these over. Now, I could go through a big spiel about it, lots of algebra, lots of arithmetic. But there's actually a very simple premise and a way to think about it, to generalize it for n roots of an equation. Let's use the same logic that was down there behind the Moraras Theorem, and what we're going to do is take the argument and essentially divide it into n parts. So that previous one, z squared, we'd be dividing it into 2 parts. We want 2 solutions. What we're going to do is start by extending the range of our arguments from negative n pi to pi. Doing this allows me to expand it and get all the solutions in that extended range, and then simplify it down to get my range from negative pi to pi for the argument of my final solution when we divide through by n. So say I was to do the previous one, I'd have n equal to 2, I'd be dividing it into 2, so what I'd do is I'd study all the arguments between negative 2 pi and 2 pi, and then what would happen is as I'm dividing through by n, using the Moraras Theorem, I would then bring it back into the range of negative pi to pi. So essentially we're saying, right, let's split it up and use a bigger range, because then when we divide it, we bring it back into the smaller range. It's the premise of if you're solving an equation, let's say we had y equals sine of 2x, and we were originally told that x was between 0 and 360 degrees. Well, the way that we'd want to solve this is we'd extend the range, get all the solutions in the wider range, and then bring it back down into this shorter range that we were originally given. It's the same premise as that, we're just using the Moraras Theorem to extend. So let's imagine we've got z equals r cos theta plus I sine theta. Then n solutions to the equation z1 to the power of n, which equals z, we get them by performing this calculation here. So z1 equals r to the power of 1 over n cos of theta plus 2k pi over n plus I sine theta plus 2k pi over n, where k is 0, 1, 2, 3, all the way up to n minus 1. So for the k, it goes from 0 up to 1 less than the number of roots we're having. So if we went again back to the previous example, we know that n is equal to 2, so k would be 0 and 1. That would give me my 2 solutions within the range that I want, and then that would give me the answers. Now, one thing to note is if we were to sketch this, the position vectors of the solutions, they would divide the circle that our polar form represents of radius r with a centre at the origin into n equal sectors. So again, the previous example would split the circle into 2 equal sectors, which would represent our 2 answers. Now that's a lot of information to throw at you. I mean, that's a big spiel. It's the kind of thing where if I sit here and explain it to you, you'll scratch your head and wonder what I'm going on about. Best way to do it is to demonstrate with a couple of examples. So let's go back to what we were looking at before. Let's go back and explore the solution of the z squared equals cos of pi over 3 plus I sine pi over 3. So I know if I've got z squared is equal to that, if I take the square root, I get z equals cos of pi over 3 plus I sine pi over 3. So I'm looking for the square root of that. So I'm looking for that to the power of a half. Now that's great because we can think to ourselves, right, there we go, just take the square root, job done. But no, remember, we're going to have n number of solutions, so we're going to get 2 solutions for it. So what I have to do is generalize it and actually say that I get my solutions, z, by doing cos of pi over 3 plus 2k pi, then plus I sine of pi by 3 plus 2k pi. And what that does is that then extends my range to cover all of my solutions so that when I have my power to the half, which I'm going to take in using the Moraras theorem, I then bring it back into the range I want and I can get the correct solutions that I'm after. So if I bring it in using the Moraras theorem, this power of a half goes in and multiplies each of these brackets here. So I'll then end up getting cos of a half times the pi over 3 plus 2k pi, then plus I sine of a half times pi by 3 plus 2k pi. So what I then do is multiply in these brackets and simplify, and then look for my k's, use them to get my solutions. So then I can say, fine, so my solutions for z are given by cos, and then multiply this bit in the bracket of pi over 6 plus k pi plus I times sine pi over 6 plus k pi. And what I can now do is go through the number of k's that I want to get my solutions. Now remember, k goes from 0 all the way up to n minus 1. So I'm going to investigate in this one is k equals 0 for my first solution and k equal to 1 for my second solution. So if I've got k equal to 0, I'm going to go for my first solution, I'm going to call that z1. What I know is if I substitute k equal to 0 in both of these, well, that's going to give me cos of pi over 6 plus I sine of pi over 6. Second solution is if I substitute k equals 1 in both of these, I get pi over 6 plus pi in both of these brackets. So what I'd end up with is z2 is equal to cos of 7 pi over 6 plus I sine 7 pi by 6. Now, if you look at this and think about the original conditions for writing in polar form and solving from there, my range in this had to be between negative pi and pi. So it had to be in that range there. Now that we've started to find our solutions, this condition applies again. So I have to make sure that whatever I'm taking cos and sine of is between negative pi and pi. And if it's not, I do the same thing I did before, subtract 2 pi or add 2 pi depending on the sign of it to get it back in that range. So in this case, 7 pi by 6 is out with our range, so what I'm going to do is I'm going to take away 2 pi from those, i.e. I'm going to take away 12 pi over 6 from those, and I'm going to end up getting cos of negative 5 pi over 6 plus I sine of negative 5 pi over 6. We can then simplify that using the rules that we know, and what I end up getting is I get cos. Remember, what I've got to do is look at the signs, so because it's negative with the cosine, I just ignore that. So I'd get cos of 5 pi over 6, then this minus goes out in front, take away I sine of 5 pi over 6. So it's a few steps that we need to follow in order to solve these sorts of equations and these sorts of questions, but if we follow this generalized method, we'll be able to do it. Now a key thing is remember this bit here, as I've shown you in this, has to be written in polar form. If it's not, turn it into polar form, then do the work from there. Let me show you. Let's imagine I wanted you to solve the equation z cubed equals 4 plus 4 root 3 times I. So what I do in order to solve this, first thing I have to do is turn it into polar form. Now remember, for polar form, we need r and we need theta. So in this case, r is equal to the square root of 4 squared plus the 4 root 3 all squared. If I do that, I end up getting square root of 64, which gives me 8. Theta is then equal to tan minus 1 of y over x, so 4 root 3 over 4. If I do that, what I end up getting for theta is I get pi over 3. So then my generalized set of solutions for this one is going to be z equals 8 cos of pi over 3 plus 2k pi plus I sine of pi over 3 plus 2k pi. This time though, because it's cubed here, I'm taking the cube root, so it's going to be to the power of a third. So what I'm going to do is 8 is going to be to the power of a third. I'm then going to multiply both these brackets in here by a third and start looking at my case. So I'm going to end up getting is z equals 8 to the power of a third. That's cube root of 8, which is just 2. Then it's going to be bracket cosine of 1/3 times the pi over 3 plus 2k pi plus I sine of the 1/3 times pi over 3 plus 2k pi. So simplify what's in the brackets here, and I get my conditions I'm going to be looking for. So z equals 2 bracket cos of pi by 9 plus 2k pi over 3 plus I sine of the same thing. Pi over 9 plus 2k pi over 3. What I can then do is start to look at different values of k to give me my different solutions. Now, to the power of a third, cube root, so I'm going to get 3 solutions. In order to get them, I look at k equals 0, k equals 1, and k equals 2. We substitute them in, we get our answer from that, and then we see where we go. So if k is equal to 0, what I end up getting is my first solution, z1 equals 2 bracket cos pi over 9 plus I sine pi over 9. If I substitute in k equal to 1, that's going to give me pi over 9 plus 2 pi over 3 in both of these brackets here. So it's going to give me my second solution. Z2 is going to be equal to 2 bracket cos of 7 pi by 9 plus I sine 7 pi over 9. And then my third solution I'm going to get when I substitute k equal to 2. So Z3 is going to equal 2 bracket cos of 13 pi over 9 plus I sine 13 pi over 9. Now remember, has to be between the range of negative pi to pi, so we take away 2 pi from these in order to get it back into that range. That gives me negative 5 pi over 9, so I'll then simplify it using the rules, and I get 2 bracket cos 5 pi over 9, take away I sine 5 pi over 9. So the steps are actually fairly simple to get the correct number of solutions. Just remember, you're going to get the same number as there is the power. Follow those steps through.